this the wrong one? It should be. Oh, doesn't matter. Shit, how do I get to the first one? All right, that was my fault. Okay, does this work?
Okay, so it's my pleasure to introduce Martin Stoll. He's a professor at the Technische University of Chemnitz in Germany. He mainly works in numerical analysis, numerical linear algebra. He has looked a lot into efficient solution methods, fast solvers, low-rank methods, and conditioners. The applications are optimization and optimal control, image inpainting, I think, and more recently uncertainty quantification, so PDEs with random coefficients. And I'm not sure he's going to talk about it today, but sorry, I didn't look at the abstract. So the title of the talk is Low-Rank Methods for PDE-constrained Optimization. Please, Martin.
Thank you, Elizabeth. Also, thank you for organizing this or carrying a lot of the workload, as it seems from what I've seen. Thanks the program organizers for having me, for the nice dinner, the beautiful location. All right, so I'm a linear algebra person, and similar to what Lars was saying, I'm not an expert on all aspects of UQ. So I'll talk about a lot of stuff involving matrices today, and this is joint work with Sergey, who's talked yesterday, and then Peter Akum, who was a PhD student, doing a lot of the work on the optimization with PDEs with uncertain coefficients. And then very recently, I'll only mention this briefly, we have a postdoc, and I'm never able to pronounce his name properly, so I always say UQ, which is good because we're working on UQ problems. All right, so the topic of my talk is optimization. So we have, this is a very generic, general slide. We have some objective function that we want to minimize, and we have some constraints linking what you can think of. So in my world, so far U is the control, and Y is the state. If you are in a statistics problem, you will probably think of this as the parameters, and you think of Y as the observables. And so then there's some constraints, and these are usually something that maps the control to the state or the parameters to the observables. All right. So just you can guess the outline from here. I'll talk a lot about the model problem, then the curse of dimensionality, and eventually I'll add UQ. But I want to spend a lot of time on the basic setup. So here is the setup that we want to consider. So we have some objective function, which means I'll bring my function y, which is I call the state. I want to bring this close to something that is the desired state, like the heat profile in the room or something that shit, so all right, I'm sorry, I'll try to avoid this and talk quicker. We have here the state that we want to bring close to something, but there comes a cost associated with it, and the cost is usually found via this control term, and we penalize this here in this objective function. You can think of this, if you're an inverse problems person, as a Tikhonov type parameter, that is beta. All right, so and then you have the boundary conditions that should reflect the physics of the problem and so on. So then there are several approaches, and the question is always, how do you proceed, right? So I have to admit now that I will work with discretizations, and they will be fixed. So one of the routes that you can take is you discretize everything, and then you optimize it. Or, I don't know what. I can see the screen here. I don't know what I'm doing wrong. So I can optimize also the infinite dimensional problem and then discretize. Ideally, those are two routes that lead to the same problem that you have to solve on a discrete level. This then depends on what is the discretization, what is the optimization, and so on. The computational bottleneck, fortunately enough for me, is almost always solving a large and sparse linear system. It could also be large and dense. That's even worse. Right? So how do we get to something like this? So now I discretize my objective function. So M is some matrix because I use finite elements. This M stands for the mass matrix, so that's common notation. And these will now be vectors. So I just use the same notation, but they will now be vectors of whatever degrees of freedom I choose in space. And then I discretize my PDE here with finite elements. You can do something else if you like. Then K becomes the discretization of my Laplacian. And to link to a statistics problem, you now can think of this also as this. If you put the K to the other side, it's invertible. If the boundary conditions are right, then you have something that maps the parameters to the observables. And then this you can think of as a map estimator problem, right? So this is PDE-constrained optimization, but same algorithms apply. So what do you do to solve this? You write down a Lagrangian function looking like this. You take the derivatives with respect to all the variables that you have, y, u, and p, and you write the first order or KKT conditions down. And what you see is a so-called KKT system, which looks like this. And systems like this you'll find if you've worked on PDEs in the past, and this looks a lot like something that when you discretize a Stokes equation or Navier-Stokes, then you have something that has a block A here, you have a constraint block B, and then you have the transpose of this there. So this comes out of the discretized and optimized approach. Then this is a symmetric system. The optimized and discretized is not necessarily symmetric. But then again, we have to solve a linear system, and to link to the first talk of the conference, we're never ever computing the actual inverse, but what you do is you apply the matrix or the operator to a vector. So this is how every Krylov solver, CG, or simple iterations, everything just applies this to some vector. All right, but who cares about steady problems? Most people in PDEs, not. So this is why we moved on from one fruit fly problem to the next. So we went to the heat equation. It's only slightly more difficult, but it reveals more structure in time-dependent problems. The idea is the same. You want to bring this guy close to this. I would like it to be quite cold up here because I'm moving around and I'm nervous, and you might be a little cold up there. So this could be the desired state, right? So, and then you link again the control, the heating that's on the wall, or the draft that goes out of the window. You link this via the heat equation here. So a parabolic PDE, and you discretize again. Now, it's a little crazy in the beginning, right? We discretize everything. We discretize in space and time. And again, apologies. This was seems to be an unstable talk. So now this guy is a very, very large vector, right? It consists of many vectors of spatial dimension. So you have one of those has the dimensionality, let's say 1,000,000 degrees of freedom in space, and then we have 1,000 time steps. So this will be very large. But don't worry. All right, then I do the same for my PDE operator, right? So you start with your favorite scheme for solving an ODE, which is implicit Euler, or something else, and then you see that you have the discretization here in time, and then you also need to discretize in space, and then I say I'll plug everything into a gigantic linear system, right? You can see this nicely here, that this is implicit Euler. If you take the matrix times vector, you see that this gives us my2 minus my3, and then we have the stiffness matrix with a time step parameter here. All right, of course you never actually, you know, if you would be naive, you would plug the system into MATLAB and then use backslash, and then you could go on a very long coffee break, right? Or you get out of memory. But you can be much smarter. Again, you get a linear system that looks like this. Sorry, this is not 1/2. It's a block diagonal matrix. This is a very, very large system. But all you need to do is multiply with that matrix or apply the operator. And the operator consists of very simple ingredients: a mass matrix and a stiffness matrix. The same you need to store for the steady problem, right? So the storage matrix-wise is not necessarily more involved than for the steady problem. Just the storage of these guys here. All right, we can prove then you need the preconditioner, and you can think of the preconditioner being good if it's something like representing the right spaces. So you can you can think of it as the Riesz representer of the appropriate spaces. If you like more from the matrix side, then you just have something that is a block diagonal matrix that keeps this block, sorry, the 1/2 here needs to go, it's just a 1. Then the same, you keep this unchanged, and then you have this really ugly object. So the ugly object is the Schur complement of this matrix up here. I didn't even write it down. And the Schur complement is a sum of complicated operators. And inverting a sum is quite difficult, so what you can do, you can cross out terms. That works, but it's not necessarily very robust. Or actually, well, here it is in the theorem. This is the ugly thing, the Schur complement of this matrix, right? So what you can cross out this guy, but then you lose some robustness. You can cross out this guy. But what you can actually show, sorry, what you can show in the nice setups is, then you can prove it. It also works in the not so nice setups, but then it's more difficult to prove, is that you can approximate this guy by this product. And this product is just a perturbation of this block triangular matrix. And this is, you need to multiply with that, and then you need to invert that if you want to apply the inverse of this guy. And for those who come from PDEs, this means it's very simple, because this guy here is a block triangle matrix. And you only, in a precondition, only need to approximate it, right? You don't need to be accurate. So inverting a block triangular matrix is easy, right? Even for blocks, you just do something that resembles the inverse of this, so like a multigrid. Or you do some simple iteration or whatever. So this is almost for free. And so here are the results, and they motivate the second part of the talk is, all right, we see, so these are the degrees of freedom in space. So just one of the components has this many entries. And then we have 20 time steps. So that's not a lot. So what we see here is that we vary this parameter beta, which is nice to see, so that it's robust and so on. And what you see is that the iteration numbers of my method, this is called MinRes, it's one of the, or I would say the method of choice for KKT systems that are symmetric. You see the iteration numbers are constant, 10, 10, well, there's 1, 8. No one complains about, that. So we see they are robust with respect to changes in beta, and they are robust with respect to changes in the degrees of freedom. And then you see the blue bit, and then you see what we've seen many times here is the curse of dimensionality, right? So now that's a good exam questions. Is this a 2 or 3 dimensional problem if I don't show the first column of this matrix? If the algorithm scales perfectly, right? If you do uniform refinement, then the matrix essentially in 1D it doubles, in 2D it grows by a factor of 4, and in 3D it grows by a factor of 8. And you can see this nicely here in the numbers, right? You have to apply the matrix, and it's 8 times more expensive. So this is a 3D problem. So this is what people, this is what happens when you do this uniform refinement, right? And this also what means that the vectors will grow quite a bit. But this is not such a, so the answer is not to buy a bigger computer, right? You could do that. You can apply for a bigger machine or some supercomputing hours, but I like to quote Philippe Twant on this one, is that I rather have today's algorithms on yesterday's computers than vice versa. So the answer comes from algorithms here. And so the algorithm is helping us to break this curse of dimensionality. Of course, it's also good to get a new computer, right? So you should do both. And this is a very simple observation where much of the pioneering work, here's a reference to last, kind of a long time ago by now, is if you just look at the most simple equation that you do in numerical analysis when you start talking about PDEs, it's just a Poisson problem in 2D on a unit square. And then you see you can discretize this guy with finite differences, and you see this Kronecker product structure. So what does this mean? That means you have here a one-dimensional identity, a one-dimensional differential operator, and so on. And what we do in mathematics, we always write this matrix. You even implement it like this, but then you consider this to be a vector that you number 1, 2, 3, 4, and so on, right? But what it actually is, it's a problem in 2D, so it's actually a matrix, right? So then comes the idea, well, why don't I consider this, right? Rather than being a long vector, I'll take the vec operator, which means I have the solution as it sits on my spatial domain. What I then do with the vector is I cut it up and glue it together. Or I do the opposite. I don't actually go to the vector, but just consider this X to be a vectorization of a matrix. And now comes the nice story, the same for the right-hand side, right? Because X we don't know. The same for the right-hand side. If the right-hand side has some low-rank structure, so it's some matrix of this form, which for a forward problem not always clear that it is of that form. Can you do anything with it, right? You can write it like this, but is this any useful? And so we hope to explore the low rankness that comes from the right-hand side and push it to the solution, rather than saying, all right, I'll compute the solution, and in the end I'll do an SVD of the solution, and then I see, well, the rank was 5. Right? What you want to do is you want to start with something that is low rank, the right-hand side. It's not always clear what that is, but if it is, then I never want to leave that space. Right? I want to do whatever my iterative solver is, just maintain this in some form. And now we go back to whatever your favorite solver is for a linear system, whether it's a simple fixed point iteration, Jacobi method, Krylov solver. What they do is they multiply with the matrix. So now I assume this guy, then the power of the SVD comes in. We've seen this many times here. We only need to do this, and the power of the SVD comes in. So I assume that my current iterate is of low rank form, which is like written like this. So this is a very tall and skinny matrix, and this guy is short and fat. Right? So now the question is, can I maintain the tallness and the tall and skinny and short and fat? Right, if I apply my matrix. And then if, this is my A, I apply this using the rules of these operators, I see that the result, which is all you need to do in a CG algorithm, looks like this. So this is still, this is short and tall and skinny, but this guy is not quite as skinny anymore, right? And this is short and even fatter, right? So the question is, can we, again, then comes the not so free lunch bit. You can truncate this down, hopefully, and then you maintain that in the next iterate, if this is k plus 1, this will be k plus 1, and this will actually be, again, tall and skinny. So this is the very simple but very powerful observation. And then you have to truncate. That's the bit that's not for free. Right. And you can do this also for my optimization problem, so this might be a little bit more technical. So you can write this, and then you get this kind of, this Kronecker product is your enemy because it tells you that the structure really, that the dimension really hurts you, right? But it's also your friend because you can use the structure. So we see this is the same system we had before. This is my objective function in a discretized setting, and this is my PDE. It looks a little scary, but it's actually not that bad. And then I'll use the same notation. This is my unknowns. So remember, those were crazily large, right? But I now glue them into a matrix and into another matrix. And for my matrix, there's the old friend, the SVD. And I hope to maintain the structure. And this is probably the most technical slide here, is that can the matrix vector product with this ugly matrix maintain the structure? And in fact, it can. These guys are, again, tall and skinny, and so on. But then I have to do some form of truncation to maintain that structure. And the question now actually is, does that work? I mean, in the forward equation, I just want to make some comments. In the forward equation, it's not always clear to me that you should have a low-rank solution. It depends on the operator and on the right-hand side. In an optimization problem, most of the time, the desired state, which goes, I don't have it here anymore, here, which enters the right-hand side, right? So it has the same role as B, is something boring, right? You want the flow around your car or your airplane not to be turbulent. This is not the desired state for something to be turbulent. If you want something to change rapidly or have a lot of turbulent structure, then this is probably not the right approach. But if your desired state is to maintain a constant heat here and a constant heat there, or some rather, maybe a periodic flow or something, then the right-hand side will be, in a sense, low rank, a little boring, maybe, and then this is a valid approach because you drive your optimization problem towards this low rank solution. You can do this, of course. Then the question is, again, if you talk to PDE people, okay, heat equation, that's all fine. You can do this for the Stokes equation, which is slow of something that's very viscous, like honey. Convection diffusion, there again it becomes more difficult because the ranks, depending on the influence of your convection and so on can grow, but it still works. I think everything is a little bit more difficult when things become nonlinear. So with Sergey and I, we've done this for Navier-Stokes, but I'm not really sure this really works well for reaction diffusion systems like a Cahn-Hilliard system or something like that. You can do different types of discretizations in time if you prefer Crank-Nicholson or BDF or whatever your favorite method is. You still need to worry about something about preconditioning. This doesn't go away. You can rely on very well-established methods for Sylvester equations that you need in the preconditioning context, but you still have to use some form of, let's say, multigrid for a classical PDE operator. And in certain cases, we can actually prove that this works. All right, so these are actually the first results that I ever got for this, so they're a little out of date, but they just illustrate the performance. Just ignore what the technical terms here. It means this is the low-rank solution, it's the full-rank solution. I implemented this not in the most sophisticated way, so these numbers should actually be better than they are. But eventually, when I refine the temporal mesh, the spatial mesh stays the same. Eventually, I get out of memory, right? And this will happen. So you just refine in something in some space, and then essentially the dimension doubles or quadruples or whatever. So eventually, you run into this issue with out of memory. So this is essentially what the key message is, that this allows you to, do a big computation on a laptop rather than on a supercomputer. And the ranks, this is one of the interests. The second row are the ranks of the components y, u, p, and you see that they actually don't grow that much. Again, this depends on the application. So now I have that uncertainty. So this was the work that I've done a while ago, and then we had this PhD student who wanted to see what happens when you consider a PDE. Like I think we've seen this one before, where we assume now that this coefficient here is uncertain. So it's not it's a PDE with an uncertain coefficient. So this is the expected value of this difference here, and we included the standard deviation. Someone mentioned that this would be a good idea, but essentially the problem looks very similar to before. We have some desired state, and then Elizabeth gave an overview of the different types of objective functions. So you can consider, and there's a battle if you are in an audience with some people, they would say the control needs to be deterministic, other claim it needs to be stochastic. The methodology applies in both cases, so I think I stay out of that fight a little bit. So again, this is a problem now that has a temporal component, the stochastic component, and the spatial component of the PDE. And here are some of the assumptions. So the classic, we do some expansion in the KL expansion or polynomial chaos of some dimension n. Right? And then we have, again, this doesn't need to be linear finite elements, but this is for the Poisson problem, that the heat equation problem, something we do. And again, we use the implicit Euler, but we're not tied to that. And so then we went to the stochastic Galerkin approach, and the stochastic Galerkin approach leaves you with a very large linear system. Right? So this is, you can reuse you can copy from slide to slide. It's the same problem. It's always a saddle point problem, but the individual blocks become much more ugly. Right? Here you have something. You have this tensor product structure now. This is the temporal component. These are matrices coming from the expansion for the KL expansion, and then again there's a mass matrix coming from your discretization in space. The same for your PDE. This now has more involved. You have some of these stiffness-like matrices, but the structure is again very, very similar. And again, the techniques you can use are very similar. So I first saw this problem a long time ago. I think it was Catherine talking about this in Bonn. So there are a lot of people who have worked on stochastic Galerkin methods and preconditioning, and I'm sure I'm forgetting some. At least I'm covering a lot of them that are sitting here in the audience. And they've actually provided a really good starting point for us. Right? So again, this is the problem. This is what you want to do. And then you can prove something. Again, in the nice case. In the more ugly case, it works, but it's more difficult to give a good answer, a satisfying answer for all the possibilities. Just not to get into the technicalities, what you see is that the approximation to the Schur complement, which is of this form, it looks ugly, but it actually is not too bad. It's something that you can easily do. provides you some robustness with respect to changes in the parameter. And then we've implemented this, so we went to the tensor world. A lot of it is due because we had access to Sergey, who is the key developer, I might clear, of the TT toolbox. So which is what we use. So essentially we're using the TT toolbox and hence the TT format. It's the approach is not tied to that. It's just if you're not an expert, if you come to the world of tensors, you rather, I didn't want to write my own toolbox, so I wanted to rely on something. So we used this. So we've seen this before. You have this, actually these, just 3 in this case. And then we have these tensor trains here, and the same representation for the matrix operators. All right, and here's Akkum's first example that he considered. Is I'm just highlighting something was this more simpler problem of the heat equation. Is we have some where the dimension goes from 10 million to 80 million, and the time goes from like 300 to 380 seconds. And then again, the problem is we have so many parameters, and if you want to talk about iterative solvers, you always want to show it's robust with respect to all the parameters. So you have to show results for your random samples in the tensor of parameters to see whether it actually performs well. So this is implemented in TT MinRes, but then again, Krylov solvers, there are more sophisticated schemes that maintain a lower rank of the solution. So just to illustrate that this is not tied to methods to kind of just simple PDEs. And they're still complicated, but you want to, if you want to convince someone that this is a more general technology, we move to something that's called the Stokes-Brinkmann problem, which is a mixture of a Darcy-Stokes problem, and you have some nasty coefficients in there. The thing is now you have to consider something that's not just the straightforward linear finite elements. We relied on something that's called a mini element, and we actually used Phoenix, which is a C++ tool with a nice Python interface to discretize this equation. And again, we use this in an optimization setting. So here we assume that this coefficient here is a random variable just in the simple form here. And again, you do this, you discretize in all of the dimensions, and you end up with something that looks is the discretized function, and then you have the discretized PDE, but now every PDE operator itself is a saddle point problem. Saddle point problems are symmetric and indefinite, so they are harder to tackle than just your run-of-the-mill Poisson problem. Again, you see that these operators here, this is the implicit Euler, and each of those guys has a lot of structure here, right? This itself is a Stokes type problem. Okay, and then, but again, once you collect all the notation, you end up with the same type of system again. And again, we have a preconditioner that has a certain structure, whether it's of this form, or you ignore the minus and this and make it a block diagonal matrix. It's not quite so crucial. The show complement, again, is of this type of form. This is, again, the complicated operator. And these operators are usually more easy to invert. They rely on well-known ingredients. Again, something like multigrid and so on. And this was when we experienced that the TT GMS, which I suggested we should use, that the ranks would become too large, and then we relied on Amen methods that that Sergey is the expert on, and he can explain you all the details. One of the ingredients is more for the PDE folks here is that you need a proper preconditioner for the PDE system itself, right? Taking out optimization, taking out uncertainty, you're still solving the PDE is not trivial. And you do this with a system of this form. So this is more structure within your preconditioner, and this is just a technicality that this is easy to approximate. This you can do with multigrid itself, and then you can prove some nice or show that the show complement of this PDE operator has the structure where these operators are simple, right? But and you derive them from function space arguments. All right, so here's just it's just the setup. We have something based on Phoenix for the Stokes-Brinkmann equation. And now here comes a graph with a lot of information. So I think we should rather focus on the right-hand side. And we focus here, we want to show that something is robust with respect to changes in the parameters. So we fix everything but this parameter beta. This was the Tikhonov parameter, and we let this vary from over several orders of magnitude, right? And we see that the iterations are not completely independent. This is the red curve, right? They grow somewhat, I don't know, from like 80 to 200. But the crucial bit is the blue curve, right? So this is the memory that you need for the solution of this problem, right? Compared to the memory if you would have to solve the full system. So exploiting the low-rank nature, you never go above 1% of the storage that you would need for the full problem. So you have achieved quite a bit of compression. Okay, that was quite nice. And then we varied this new parameter which increased the influence of the stochastics. So which means that the randomness, let me show you this here again. Sorry about this, and we have it. Sorry, where was it? Here it was, right? The influence of this variable here. And you can imagine that if we make this larger, then of course the problem becomes a little more complicated. And this is reflected in the iteration numbers that go from 100 to 300. And this is the only time actually we went above 1% of the storage. But again, the method performed quite nicely in terms of maintaining only a fraction of the storage that you would need for the full problem. Okay, and then I wanted to squeeze this in, which is work with UEQ. Can you extend this to statistical inverse problem? And this, unfortunately, Tan couldn't make it because this is a lot of this formulation comes out of. We noticed this problem first coming out of Austin. I know you've probably seen this many times before, but what they wanted to do is they wanted to approximate the posterior covariance matrix. And then they have here, this is the definition where all the assumptions are friendly, everything is Gaussian and so on. The parameter to observable map is linear, so you call it A. I thought that looked good until I realized that A actually means the inversion of a PDE, right? So you hide this nasty fact in calling it just A, right? So this is a complicated problem. Even if your PDE is sparse, right? This will be K inverse. Nothing is sparse anymore. These guys might be nice, right? But then you have the inverse of this nasty guy, right? So again, this relies. I didn't give a reference here. This is this notation I've stolen from Gatas and co-workers. And then they massage this. I think then you can call this prior preconditioned. You just take something out and you look at this guy, and this guy they then call the misfit Hessian, which again is, looks like this, but this again, let me remind you, this involves solving a time-dependent PDE problem, right? Nicely hidden in the fact that you just call this A. And then what they do is they approximate this they compute the eigenvalues of this operator, which for someone like me who comes from linear algebra, you do a Lanczos or Arnoldi algorithm that just multiplies with this operator and then computes an eigenvalue approximation or eigenvector approximation to this operator. But again, these guys here live in space and time if this is a space-time problem, right? So this is solving, just multiplying with this operator, which you have to do. Multiplying with this operator is very costly because you have to solve, every time you apply A and A transpose, you have to solve a time-dependent PDE. So again, if you have structure in the problem, like the one I mentioned before, this is the comment I just made. This is high dimensional because it's a parabolic problem. So I'm being very brief, so if you are more interested in this, we should talk over lunch, and it's lunch soon. I try to stay on time. These guys are large. The eigenvectors here live in space and time, and you might need quite a bit of them. You might need, I don't know, several hundreds, right, to reflect this one, which means you have to solve PDEs many, many times, right? And so what we said is, okay, if the PDE has a certain structure like the one we had before, then you can approximate, this is a column of this eigenvalue matrix for the misfit Hessian is again nothing else than the vectorization of some matrix. If I have a matrix, my friend the SVD comes along and I'll approximate it by a tall and skinny and short and fat matrix. And can I maintain that structure? And the answer is yes, I can. And This we do by an Arnoldi procedure that we've implemented in, again, in the TT format here. And you can actually see that you can nicely reduce. I mean, this is a great reduction here already, right? From something that lives in a space of, I don't know, a gazillion variables maybe, to something that is maybe several million or something. And we exploit this structure even further by compressing the columns of this eigenvector into spatial and temporal components. Right? So you might be able to do it again on a laptop rather than a big machine. Again, this depends on the structure of your PDE and what your parameters and so on are. All right, so this is just to tease you. If you're interested in this, talk to me afterwards. To just conclude that the Krylov solvers that just need to apply the matrix, the operator, they provide a very nice tool for these large-scale linear systems. Preconditioning is still essential. Right? It means whatever the problem is, you need to approximate the PDE in some form, and you need to use ingredients that have been around for a long time, something like multigrid, something like a Jacobi iteration, whatever you like. The curse of dimensionality can be lifted. Again, it's not a silver bullet in all cases, right? It's like in PDE-constrained optimization, people like to squeeze the control between 5 and 7, right? Or something, it needs to be positive. And this is something where I think there's a lot of work to do. Whether you actually have a low rank, it's not quite clear to me. This could be quite difficult. Then again, for nonlinearities, we've done this for Navier-Stokes, and that works. But for something that is of, let's say, reaction diffusion type system, I don't know. I mean, maybe a question for all the tensor people here. What you'll do with the nonlinearities? You can apply these methods to quite some challenging problems. And with that, I'll thank you for your attention.
A question on slide 22. You showed us the results for your low-rank compressed solution, and I was not completely clear what are the variables that you separate in the TT format. Is this space, time?
So yeah, here it's space, time, and stochastic space. I don't know what I should call it. Yeah. So we have the three. We have the PDE, the spatial dimension, the temporal dimension, and let's call it the stochastic dimension.
But still, I mean, it looks like when you increase the degrees of freedom, that you have a sublinear scaling. I mean, you look at the scaling from 10.6 million degrees of freedom to 85 million degrees of freedom, and the increase of time is just a little bit, although you take more steps. So do you exploit more structure? Do you use some QTT approximation?
No, certainly no. This was before Sergei, so I don't think we could handle QTT before Sergei. So no, I think we're just doing simple. I don't know. I don't have the answer to that. I mean,
you separate into three components.
Yes. So the PDE we never wanted to separate because if you, like in the Stokes-Brinkmann case, you might not want to use. You might want to bring your own idea or the PDE might have some natural discretization that, like the mini elements, let's say, or you want to have a certain type of you want to do Q1 for your Stokes or something else, right? So this is why we never. The PDE was a block, the time was another block, and then the kind of the KL gave the other block. But I don't have the answer. I can look.
In your last example, in the work with UAQ, you approximated the covariance matrix, is that correct?
Yeah, this posterior covariance matrix.
Okay, and you constructed like a low rank approximation.
Yes.
I mean, yesterday we had a talk about that you have to be careful when you approximate covariances to maintain positive definiteness. I mean, can you maintain it here? Is that guaranteed or not?
I assume so, but I haven't. I'll look into it. I don't know. I guess that well, if you, I mean, this is this guy here will be positive definite, right? If lambda is positive definite, I don't know whether we observed any negative eigenvalues. I don't think we ever did. I mean, but I don't know whether it's impossible to. I mean, it depends. If would your Arnoldi process give you a negative eigenvalue? I don't know. Something to look into.
Okay, thanks a lot. Well, yeah, I don't see more hands raised. So let's thank Martin.